Good day to you. Once again, we're still in the electric circuit chapter, and this question states, what is the equivalent capacitance of this closed circuit? Now, what we're dealing with here is we're actually dealing with capacitors, not resistors, and thus you can see that the symbol of a capacitor is going to be these two vertical lines, all right? So we have a closed circuit in which we have 6 microfarads, 8 microfarads, 12 microfarads, and 4 microfarads. I want to give you a brief review about how you deal with these capacitors as opposed to resistors. It's going to be the complete opposite. So if we happen to have capacitors that are going to be parallel, as we see in this case right here, we're going to deal with those by simply summing up the total of all the capacitors. So basically their capacitance, we're just going to add them up. This is going to be analogous to resistors in series. Remember, in resistors in series, we simply just add up the resistance. When we're dealing with capacitors, we're simply just going to sum up the capacitance. If we have to deal with capacitors in series, so this is capacitors in series, we're going to take the inverse. So the total capacitance that's going to be in series is going to be equal to the sum of the inverse of the individual capacitors. All right? So the sum of the inverse of the individual capacitors. So the first thing I want to look at here is that we've got this parallel, or these two capacitors are going to be in parallel. So the two capacitors are going to be in parallel. So if we look at the oops, there we go, I wrote resistor, we should write capacitance. If we're going to look at the capacitance in parallel, it's going to be equal to the 8 microfarad plus the 4 microfarad, and that's equal to 12 microfarad. So these two capacitors in series is equivalent to 12 farads. That allows us to now rewrite this as 3 capacitors in series, and this is going to be the 6 microfarads from this one. This is going to be now our 12 microfarads, which we just solved for, and now we have yet another 12 microfarads from this one right there. Now our capacitance in series is equal to 1 over 6 plus 1 over 12 plus 1 over 12, which is equal to 1/6 plus this now becomes 2/12, or this is equal to 1/6 plus this becomes now 1/6, or this is going to be equal to 2/6, all right? Or this is going to be equal to now 1/3. So 1 over the inverse of the total capacitance in series is going to be 1/3, or we can say that the capacitance in series is going to be equal to 3 microfarads. Okay? All right, for the next problem we've got, it states an electronic flash unit produces the flash from energy stored in a 750 microfarad capacitor. The recharging time constant is 3 seconds. A, what is the resistance in the circuit? B, how long does it take to fully recharge the flash unit? Okay, so let's write down a little bit of information that was given to us. We know that the capacitance is equal to 750 microfarads, and the time constant, which is tau, is given to us as 3 seconds. And we are asked to find the resistance in this closed circuit. And so our resistance is equal to tau divided by our capacitance. And if we write this out, this is going to be 3.0 seconds. All right. Now they gave it to us this as microfarads. So if we convert this into farads, it's 750 times 10 to the negative 6th farad, because there is 1 million microfarads in 1 farad. And so this is going to be equal to 3 seconds divided by 750 times 10 to the minus 6 farads. And if we do that arithmetic, this is going to be equal to 4,000 ohms. 4,000 ohms. All right. Now it says, how long does it take to fully recharge the flash unit? So basically, you're going back up into or charging that capacitor. And so time is equal to 5 tau. And so if we put our tau in there, which is 3 seconds, it will be 5 times 3.0 seconds. And this is equal to now 15 seconds. So it's going to take 15 seconds to charge up that flash, or the capacitor that allows the flash to go off. All right? In this question, it states, an RC circuit is used to control a pacemaker. A pulse is generated every time a capacitor loses 63% of its charge through a 1.8 mega ohm resistor. The pulse rate is to be 81 pulses per minute. What capacitance is required? It also says losing 63% of its charge represents one time constant, the time between pulses. All right. So now we want to find the capacitance. What is the capacitance required? Well, our tau, our time constant, is going to be equal to the 60 seconds, basically the 1 minute, divided by 81 pulses. And doing this arithmetic gives us 0.741 seconds per pulse. So basically the duration of the pulse is going to be about 3/4 of a second. We know that our capacitance is equal to tau divided by our resistance. We know the resistance is 1.8 mega ohms. We just found our tau, so our tau is 0.741 seconds divided by our resistance. Remember, it's mega ohms. Mega means a million, so this becomes 1.8 times 10 to the 6th ohms is our resistance. Now we can find our capacitance is 0.412 microfarads. Okay? All right, for this question, it states a 10 microfarad capacitor is charged by a 10-volt battery through a resistance R. The capacitor reaches a potential difference of 4 volts in a time interval of 3 seconds after charging begins. Find the resistance. So what we're dealing with is we're dealing with the charging of a capacitor, and the charging of a capacitor is going to be an exponential function. So what we have here now is we have the voltage difference, or the difference. V naught is going to be the source. In our case, it's going to be the 10 volts. T is the time interval, and R is the resistance, and C is the capacitance. So what we're going to have to deal with is we've got to find the resistance. All right, we've got to find the resistance. So since we have an exponential function, we're ultimately going to have to take a natural log. All right. So what I can do is I can divide both sides by V naught. So I get V upon V naught is equal to 1 minus E to the minus T upon RC. All right. We know V over V naught is, we can write that out. So that's going to be 4 volts divided by 10 volts. I can move, we'll just do it right now real quick. So this becomes equal to 0.4. All right. So we have 0.4 is equal to 1 minus E to the minus T upon RC. We can move the 1 over here. And so what we get is we get 0.4 minus 1. So that gives us a negative 0.6 is equal to a negative E minus T over RC. All right. We can make this positive, make those positive. Now what we can do is we can take the natural log of all of this. oops, not m, but n. We take the natural log of all this. What we get now, let me see, let me get this, make sure I don't make any mistakes on this. We get a minus t upon RC is equal to the natural log of 0.6. 0.6. Now what we can do is, let's see here, we have a negative t upon the natural log of 0.6 is equal to r. Oops, we'll put our c right there. We can put our c right there. Okay. Now we can just fill in what we know. All right. So we know that this is going to be a negative 3.0 seconds because our time constant is 3 seconds. We know our capacitance. Our capacitance was 10 microfarads. And so that's going to be 10 times 10 to the minus 6 farads. We have the natural log of 0.6. So if you go through and do this arithmetic, this is going to be equal to our resistance. And our resistance in this case is going to equal, we just do the arithmetic here, it's 5.87 times 10 to the 5th ohms. Or we can convert this into kilo ohms, and it would be 587 kilo ohms. So the resistance for this is going to be 587 kilo ohms, or 587,000 ohms. Okay? Last problem for this chapter. It says a 6 microfarad capacitor is charged to 100 volts and then connected across a 500 ohm resistor. What is the initial charge on the capacitor? What is the initial current just after the resistor is connected? And what is the time constant? So let's write a few things down real quick. So we know that the capacitance is equal to 6 microfarads. That's the capacitance. We know the voltage is equal to 100 volts. 100 volts. Now, let's see, what are we looking for? And we know that there's a resistor of 500 ohms. 500 ohms. Yep, 500 ohm resistor. What is the initial charge? So if we're looking for charge, so this would be A. If we're looking for charge, that's going to be Q is equal to C times V. We know that the capacitance is 6 times 10 to the minus 6 farads times the 100 volts. All right, and so this is going to be equal to, it'd be 6 times 10 to the minus 4th farads. Get another color. Try pink. B asks, what is the initial current just after the resistor is connected? So let me repeat that real quick. What is the initial current just after the resistor is connected? So we're looking for current, and current is going to be equal to voltage over resistance, basically Ohm's law. We know the voltage now. The voltage is going to be 100 volts. We know the resistance is 500 ohms, and so this is going to be equal to 0.2 amperes. And now C asks, what is the time constant? So now we're looking for the time constant. And C, and our time constant is tau is equal to the resistance times the capacitance. The resistance we have is 500 ohms. The capacitance we have is 6 times 10 to the minus 6th farads. And so we do this arithmetic and we end up getting 3 times 10 to the minus 3 seconds, or we can say that's equal to 3 milliseconds. Okay? Thus ends our problems in this chapter of electric circuits. If you have any questions, feel free to ask. Okay? Thank you.